Okay, what if I told you there's a new type of computer out there? One that could, in theory, completely shatter the encryption that keeps our entire digital world safe. Well, today, we're diving headfirst into that world. We're going to look at two legendary quantum algorithms, Grover's and Shor's, and really get into the incredible promise and, the much tougher hardware reality.
So let's just start with the absolute core question, right? Is it even possible for a new kind of machine to solve problems that are literally impossible for the computers we have now? The answer is a huge yes. And honestly, that's what makes this whole field just so unbelievably cool.
But how? How on earth is that possible? To get it, you got to understand that we're not just talking about a faster version of your laptop. This is a totally different way of thinking about computation itself. It's a whole new paradigm.
And here's the thing you have to remember. Quantum computers aren't faster at everything. Nope. They're specialists. They're built for certain really gnarly problems, like discovering new medicines or, cracking encryption. For those tasks, they offer what's called an exponential speedup. Think of it like this. A normal computer is trying to find a single grain of sand on a beach by checking every single grain one by one. A quantum computer gets to look at all the grains of sand at once. It's a fundamental game changer.
So how do we actually tap into that superpower? Well, it all comes down to the software, or in this case, the algorithms. And there are two absolute rock stars in the quantum world that we need to talk about, Grover's algorithm and Shor's algorithm. Yeah, this slide lays it out perfectly. Think of Grover's as the ultimate search engine. It's like finding a single marked card in a deck of 1 trillion cards and doing it way, way faster than you could classically. But Shor's is the master key. It's the one that threatens all of our encryption. See, systems like RSA rely on a simple fact. Multiplying two massive prime numbers is easy, but taking the result and finding those two original primes, that's practically impossible for a regular computer. Well, Shor's algorithm makes the impossible possible. And look at the speed difference. Grover's is a huge speed up for sure, but Shor's is exponentially faster, and that, my friends, is why it gets all the attention.
Okay, the theory is, it's just mind-blowing. But what actually happens when we stop talking and start doing? What happens when we try to run this code on real quantum hardware? Let's get our hands dirty.
So for Grover's search, you're essentially building a sort of quantum trap. First, you build this thing called an oracle. Its only job is to recognize the right answer and flip it or mark it. Then you build a diffuser, which is kind of like an amplifier that takes that one marked state and boosts its signal so it really stands out from all the noise. And then you package all that up and send it off to a real quantum machine and see what you caught.
So that's Grover's. But what about Shor's? The algorithm that's supposed to be the internet killer. You would think that coding this thing up would be just insanely complicated. But here's the twist. In a simulation, for a small number, it's actually shockingly simple. I mean, just look at this. It's basically one command. You just ask it to factor the number 15, and boom, out pops 3 and 5. It feels almost like a magic trick. It's too easy, right? Which of course brings us to the really crucial question. Because there's a Grand Canyon-sized gap between that clean little simulation and the messy, complicated reality of today's actual quantum computers. It's time to talk about hitting the NISQ wall, right? This is the million-dollar question. If a single line of code can factor 15, why are our bank accounts and private messages still secure? The answer has nothing to do with the algorithm and everything to do with the hardware it runs on. And the term you have to know here is NISQ. It stands for Noisy Intermediate Scale Quantum. And it's basically the perfect description for where we are today. Noisy because these machines are incredibly fragile. The tiniest vibration or temperature change can throw off the whole calculation and create errors. And intermediate scale because, well, we just can't build them big enough yet. We don't have enough of the quantum bits, or qubits, to tackle the really big, important problems. And this chart? Man, this chart says it all. In theory, on a perfect quantum computer, you run the algorithm and get the right answer 100% of the time. But on a real machine, well, you get the right answer most of the time. The rest is just noise, errors caused by the quantum state falling apart. It's like trying to have a very delicate conversation in the middle of a rock concert. The message just gets garbled. That's a process called decoherence, and it is the single biggest enemy of quantum computing right now.
So, let's just break it down. Here's the hard truth of today. Shor's algorithm, to factor a number big enough to matter, needs a computer way bigger and more stable than anything we have. Even Grover's search only really works for small problems right now. We're in this constant brutal fight against noise and decoherence, and we have to use all these clever error correction tricks just to get a result that's kind of close to the right answer. That gap between the dream and the reality, it's all hardware.
So what's the big takeaway here? Is this whole thing just a fantasy? Is it a dead end? No, absolutely not. What it means is that we're at the very, very beginning of this new era. The challenges we're facing today, they're the necessary steps we have to take to get to the breakthroughs of tomorrow.
So let's sum it up. The fact that we can run Grovers at all on real hardware, that's amazing. That's a huge achievement. Shor's is still a ways off, but the key is we now know it's an engineering problem, not a theory problem. We know what we need to build. We are literally in the first chapter of a very long book, and we're learning how to write it as we go.
I love this quote because it puts everything in perfect perspective. The very first classical computers were these gigantic room-sized beasts made of fragile, glowing vacuum tubes. They were nothing like the phone in your pocket, but you couldn't have the phone without them. They were that critical first step. And that is exactly where we are with quantum computing right now. So, I'll leave you with this thought. If we are in the vacuum tube era, what does the microchip moment for quantum computing even look like? Is it a new wonder drug that cures something we thought was incurable? Is it a new material that completely changes how we use energy? Or is it an AI so powerful it solves problems we haven't even thought to ask yet? We don't know, and that's what makes this whole thing so incredibly exciting to watch. Thanks for joining me.